So before we go to the orbit stabilizer theorem, let me just like motivate the idea of a coset manifold. Okay, so what is a coset manifold? Suppose you have some group G. It's a Lie group. So Lie group means that G has some parameter space, which is a manifold, right? So, and H is some proper subgroup of G. Is a proper, say, Lie subgroup, okay? So now, because G is a Lie group, if I take two elements, say G1 and G2, there is some notion of distance between them, right? There is some natural, notion of distance between them. So for example, if I take, say, G to be, say, SU2, then the manifold is S3, right? So S3 has, say, a north pole and, say, a south pole. Obviously, the north pole is not close to the south pole, right? So, there is a G north, G south. They're both in SU2, right? And it's clear that G north and G south are not nearby. They're pretty distant, as distant you can be on S3. But there would be other, elements which are in the neighborhood of G north. So for example, there would be some elements, say here, let's call it, say, G prime, very close, and G prime would be, say, G north plus something small. Okay. Okay. So all I'm trying to say is that because G is a Lie group, there is some notion of there is a notion of like nearness or farther away, some notion of distance on it, right? So now if H is, say, subgroup of G, then we can create, say, a left coset, right? So if G1 and G2 are related by, say, G1 is equal to G2 of H with H in the subgroup, then there should be one of them, should be 1. Then we say that G1 and G2 belong to the same coset, right? But if G1 and G2 do not belong to the same coset, but they are nearby, then what we can do that we can then extend that notion of of nearbyness or distance to the corresponding cosets. So meaning that G1H and G2H are also close by. Sorry, I'm forgetting how to spell. Okay, so basically what we are saying is if there is some notion of distance between, say, G1 and G2, there is some notion of distance between G1 and G2, and they're not in the same coset, then we can say, why don't we define the same distance, notion distance between their corresponding cosets? So in this way, we extend the manifold structure to the coset space. Okay, and therefore the coset space is also, this way. This way, one can extend or continue. I don't know what word to use. Extend, all the structures, naturally defined on the manifold G to G over H. Okay, and then G over H becomes a manifold. Okay. And this is going to be important because the theorem that we want to prove, which is in the orbit stabilizer theorem, here, the coset space better have a structure of a manifold, otherwise we cannot identify it to the manifold that this acts on. Okay, so this is not very rigorous, but I think at least intuitively it should be clear what I'm trying to say. Can you guys have, like, can you give me some comments or feedback on this? Like, is this, what do you think?
I think it makes sense, but it would depend on our choice of like how we define D, right? Whether or not G over H becomes a manifold.
Yeah, I mean, you have to take a G, and the G usually has like a natural metric on it. So for example, S3 has a metric on it, right? And it's actually, yeah, you have to choose G, you have to choose H. So pictorially, what is happening is something like this, okay? So we have, say, G. So this is G. Now, if I take an element in G and I apply on it, so this is basically, yeah, an element on G, and I apply to it I apply to it all the elements of H. Then I will get an orbit, right? So this is G1, and this thing, let me use a different color for the orbit. So this is, say, G1. Sorry, G1. And if I apply all the H, I get an orbit, right? So this is, say, so this is G1H. Okay. Now, if I take another element, say G2, then I would get another orbit. Okay, so now if, say, G1 and G2 are close by, so there's a notion of distance between G1 and G2, right? Now, what I'm saying is that let me just extend this notion for all the points on this orbit. So we have now another space, which I'm going to call, say, G over H. And in this space, G1 of H and G2 of H, the distance, say, between them is the same as this distance. Okay. So if they were very close, then they would be very close here. If they were very far apart, they would be very far apart here. Okay.
Would this second manifold be like a discrete set of points though?
No, it'll still be a manifold.
Okay.
It'll still be a manifold, but its dimension would be reduced. Its dimension, the dimension of G over H would be the dimension of G minus the dimension of H. Okay, because every point over here corresponds to a higher dimensional object over here, right? These are all equivalence classes, right? These are all equivalence classes. Okay. So that's all I mean is that, you know, if these two orbits are very close to each other, you know, in the original group, then they would be very close to each other in the Coset manifold. Okay. So I think I'm going to stop here. I'm not going to give you the example because, okay, I'm just going to give you a tantalizing clue is that you can use this notion to show that SO3 over SO2 is S2. Okay. And this is really what makes Lie groups so useful for studying symmetric spaces, because you can actually construct spaces with high degree of symmetry from quotients of Lie groups. So we'll prove this in the next lecture.